the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a fourth video in a series on least squares problems for linear algebra students who are currently going through orthogonality and least squares problems. We have finally reached a topic within least squares that will allow us to use all of our theory from previous work about orthogonality. We're going to apply that theory to solving least squares problems. To do so, we just need this single theorem. Let A be an m by n matrix. It doesn't need to be square, but it does need to have orthogonal columns. There's a lot of stuff we gain from having orthogonal columns. First thing that should come to your mind is that those columns must therefore be linearly independent. We're also going to let B be a vector in Rm. The least squares solution of ax equals b is x hat, where the ith entry of x hat is given by the following. Now you should recall this from all of our previous work, just this fraction right here. It's the coefficient of the linear combinations when you generate a vector from orthogonal bases. And your orthogonal basis vectors are a1 and a2 and a3 and so on and so forth. Now there's a few things I want to say about this theorem before we use it, and then we'll hop back and actually prove it. First of all, if you have orthogonal columns in your matrix, well, as I just mentioned, those columns must be linearly independent. And once you have linearly independent columns for the matrix A, then the matrix equation ax equals b must have only one least squares solution. So if this matrix equation is inconsistent, we can still guarantee we have a least squares solution, and there will only be one least squares solution. And again, that's because the columns are linearly independent. Another thing I should mention here, and this comes from our last video, but if the columns of A are linearly independent, which they would be if they're orthogonal, then A transpose A is invertible. But as I mentioned in the last video, that's actually not how I generally go finding least square solutions. I don't like to invert matrices if I can avoid it. So I don't want to take A transpose, multiply it by A, and then invert that product. It's just not something that's super attractive to me. However, the orthogonality of columns is super powerful for us, and we know that from our previous work. If the columns of A, let's just pretend for a moment that this actually has a solution. Let's pretend that this matrix equation is consistent. Well, if the columns of A are orthogonal, then we know that the entries in X are these coefficients right here. And I made a big stink about this when we learned about, or we used orthogonal columns and learned about solving systems that have orthogonal columns, that it really comes down to not having to do, let's say, inversion of a matrix or Kramer's rule or solutions by inverse of an adjoint or anything like that. We can actually reduce our work quite significantly by using this little formula right here over and over again very quickly. So hopping back to our task at hand, if you have orthogonal columns in your given matrix, well, we gain something else. The least square solution to ax equals b is x hat, where the entries in x hat are exactly the coefficients of the projections of b onto the columns of the matrix A. It's really very beautiful. Let's go ahead and use this theorem a couple times, and then we'll come back and prove it. Find the least squares solution to ax equals b, where A is this matrix right here and b is 2, 2, negative 1, by recognizing that the columns of A are orthogonal. Now we have already found the least squares solution to this matrix equation a couple different times, I think, and it was pretty gnarly. It's just they're not beautiful numbers. However, we did it, and it involved finding projections onto a subspace and all this other fun stuff. But now that we can look very quickly and note the dot product of the two column vectors here is -2 plus 2 plus 0, or 0. That is, the columns of A are orthogonal, which means we can use that beautiful formula that we just wrote down. So x hat is x sub 1, x sub 2, because, well, the matrix A is a 3 by 2. So x hat is x sub 1, x sub 2, where x sub 1 is b dotted with the first column of A divided by the first column of A dotted with itself. Let's go ahead and compute that out very quickly. B dotted with the first column of A, we get -2 plus 1, so that's a -1, minus 3 is a -4. And A sub 1, or the first column of A dotted with itself, is 1 plus 1/4 plus 9, or 10 and 1/4, or 41/4. So we find the first component of the solution to our least squares problem to be -16/41. Now to find the second component, we redo all of our work, except with column 2 of A in mind. Well, let's see, B dotted with column 2 of A, we get 4 plus 8, or 12. And the second column of A dotted with itself is 20. And we are done. That was it. That's the solution of the least squares problem for AX equals B. So it's really nice when you have orthogonal columns. You want orthogonal columns, in fact. Well, let's do this one more time. Find the least squares solution to AX equals B, where A is this matrix right here and B is 0, 1, 3, 4. It's just to give us more practice. I didn't want to just do a single problem. Well, the first thing you're going to do, I would at least, is label my columns. And note that these columns are actually orthogonal. Now, you don't want to assume they're orthogonal. You should actually show it, but that's kind of what I did. You're going to have to do that likely on an exam or something like that. And if you have a very good instructor and they're tricky, they'll give you a matrix with non-orthogonal columns just to mess with you. So don't always assume your columns are orthogonal. Now I'll just repeat what I just did a moment ago. And there we go. Our vector solution for the least squares problem for this larger system is -3/2, 2. Look how quick that goes. Very nice when you have orthogonal columns. It's, again, the end-all be-all. Really, the end-all be-all is orthonormal columns. Now let's go ahead and hop back to this theorem right here, and we're just going to quickly prove it. There's not much to it, but it's good to see the proof no matter what, because you definitely want to get some experience and exposure to proofs. So let's see, we're going to assume that A is an n by n matrix with orthogonal columns and that B is an Rm. We want to use that assumption to showcase that the least squares solution of AX equals B is x hat, where the entries of x hat are x sub I equals B dot A sub I over A sub I dotted with itself. Well, first of all, we happen to know that the least squares solution to AX equals B is the vector x hat such that A times x hat is the projection of B onto the column space of A. That's not that big of a deal. However, because the columns of A are orthogonal, we can actually write a decomposition of this projection vector in terms of those orthogonal vectors. And the coefficients of that decomposition, well, they're going to be hauntingly familiar. The projection of B onto the column space of A is just this decomposition right here. Notice those are exactly the coefficients we're looking for. And these coefficients are actually the entries of x hat. Notice what we have written here. The projection of B onto the column space of A is a linear combination of the columns of A. And the coefficients of that linear combination are these guys right here. Well, that's what A times x hat is. A times x hat is actually a linear combination of the columns of A. X hat just contains the weights of that linear combination, so x hat must consist of those blue highlighted scalars. Hence, x sub I within x hat must equal the dot product of B with A sub I over A sub I dotted with itself. That's really all I had for this video. We are done with that proof, and I'm done with this video. I hope you have a great day. I hope to see you in the last video in this series. We're going to talk about QR factorization and solutions to least squares problems. Somewhat short, so I hope to see you there. Have a great day. Be a wonderful human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause if defects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.